Okay.
All right, so where are we? So we're,
Yeah, so I'll announce to the world that I did not calculate the Néron-Severi group with the product of the Eisenstein and Gaussian elliptic curves. I did a few calculations, but I just got too busy. So I want to know, but it sounds like you did some other stuff, so vaguely akin.
yeah, I mean, in a way, that question seems really simple, depending on which viewpoint you look at it from. I mean, we were deliberately trying to make it not so simple, but maybe looking at it from first principles, which is also a good thing to do.
Well, the map, the Néron-Severi group may be fairly simple, but we wanted to see the map from that to the coherent cohomology and see what how dust-like the image was. That's the
Sure. I mean, that's one of the big things. I mean, so right.
I mean, that's not so simple, is it? I mean, is there like some quick way to get it?
Not that I know of. No, just the Néron-Severi group itself seems very straightforward. But yeah, I mean, maybe there is something very simple about when you start looking at the whole exponential sheaf sequence, the whole exponential long exact sequence, whatever you call it. But I'm still confused about that. And right, so one of our really good excuses for trying to understand Néron-Severi groups of abelian varieties in more generality and more detail is that, as you indicated, we're really confused. I'm especially really confused about what happens with the higher Néron-Severi groups, the things you've been calling higher Néron-Severi groups, and higher Picard groups, and how these all fit together in the exponential long exact sequence. And so we have a good excuse for studying these Néron-Severi groups of abelian surfaces. But since we have a good excuse, we can ignore that excuse. That's just a MacGuffin for now. And now we're back to thinking about actual Néron-Severi groups of actual specific abelian surfaces in particular, although we may get into other dimensions of abelian varieties as well. What am I trying to say here? That, well, so I don't know if you put this on the screen before at some point, but you wrote down this very informal classification that you worked out at some point, with perhaps in discussion with Todd, of abelian surfaces, an informal classification, perhaps missing a few special cases, stuff like that, but a rough informal classification of Néron-Severi ranks of abelian surfaces. So can I pose on you to bring that email up or something like that?
Sure, you can do that.
Okay, so you can steal the.
I guess I can. Yeah, okay, I can do it that way.
The screen
I almost.
Or you want to write it?
How about if I write it down? It'll take longer, but it'll help me remember.
Sure.
What's going on?
Maybe I should write it down as you dictated or something like that.
Oh, we can do it that way too. Yeah, sure. Yeah, you seem to be at least as good at writing as I am.
Okay, so
so we can either start with like the most ungeneric or the most generic.
Yeah. So
I think I can tell you what the Néron-Severi groups are.
First of all, can I think about the organizing principles here? So the organizing principles in this rough classification have to do with, first of all, the extent to which the abelian surface decomposes as a Cartesian product, or or also as a Cartesian square. The I mean, that's just more of the same. It's checking whether the two factors are the same elliptic curve. And then basically the other organizing principle is just complex multiplication.
There may be some abelian surfaces that have quaternionic multiplication in some way, but we didn't get into that. I think we actually did get into it once ages ago.
We may very well have, but
we were like talking about like the D4 lattice or the 24 cell kind of thing, but that's a little more exotic than our bread and butter.
Okay, so that's
classification. So there may be other things out there.
yes, there may be things we're missing, but we have a partial classification, partial rough classification. So let's see. So maybe I can first use another organizing principle, just the ranks. So they're all going to have.
That's a hard one because that's
what?
That's starting from the answer and working back to the question.
Sure. But I think you actually did in the email to me. I think you listed them that way. I think you listed them in order of increasing rank.
Yeah. Okay. I was okay. Yeah. It's harder to do on the spur of the moment, but yeah.
Maybe I'm cheating by just remembering what you sent in the email.
I mean, increasing the rank seems to go along with like being a Cartesian square or having complex multiplication, or even being a Cartesian product is like lesser.
And I mean, for one thing, lower rank just needs to be more generic.
Yeah, that seems to be the.
So, okay. So what are you claiming? You're claiming that it's easier to think of the most special ones first? Or, no, it seems like we should start with the least. We should start with the generic ones and then start thinking of extra things that you can add. Yeah,
I think that's what I did. That's good to do, I'd say. Yeah. So,
okay.
So let's start with generic.
And
which is the one where we don't have any examples, right? So, or maybe you came up with one.
Well, we could probably come up with some examples if we were forced to, but let's see.
Yeah.
All right, so I'll put the ranks over here. So that's the Néron-Severi rank. Right, so I think I'll just put these down as guesses at first, because that's sort of the way you sent it in the email, and then we'll talk about how to possibly really understand where these rank numbers are coming from.
Mm-hmm.
So the next thing you can do is just a Cartesian product of distinct generics. No, Cartesian product of distinct generic elliptic curves or something like that. Yeah. So Cartesian product of, well, so there were a bunch of cases in your classification that you maybe could all lump together under one classification or something like that. That sort of seemed to be the Cartesian products of distinct in general ones. It seemed like you were claiming that it didn't matter a whole lot whether there was.
No, if one of them has a complex multiplication, I think you get. Wait, do you get more? No, I'm getting confused.
I think you ended up getting rank 2 for all of the Cartesian product of distinct ones. But you listed as I think 3 separate cases depending on whether both or one or neither of them had complex multiplication of the elliptic curves. So let's say from Cartesian product. In fact, maybe I can just call this Cartesian product, with the distinct implied, and that will distinguish that from the Cartesian squares. So
I mean, the reason why I did them separately, and I think we still should, is because I think the calculation of how it works different.
Sure. Yes, that's very possible. So I'll try to leave more room there or something like that. Try to get rid of that stream on. Okay. And maybe the next one. Yeah, maybe it really did just go by ranks. Maybe the next one here is rank 3, and that is the Cartesian square of generic.
Yeah.
And then the rank 4 ones we're guessing are Cartesian. How does this work? Cartesian square of elliptic curve with complex multiplication. Oh, maybe they just call that a CM. I'll use that abbreviation. That's a CM, elliptic curve.
Uh-huh. Yep, that's what people do say.
A complex multiplication, or CM, elliptic curve. Okay. And yeah, and right, as you're suggesting, when you analyze how this is done, case 2 in particular may break up into finer cases, depending on what the factors are like. So, all right, so let me ask, again, I think I did ask this question in email, but it's not a very precise question, or maybe it is almost a precise question, but let's see. So the question is, I'm trying to understand your method for doing this. You gave some big hints, but it sounds like maybe you're suggesting that our abelian surface, our complex abelian surface has, well, first of all, we're at some point we're probably going to assume that it has a polarization on it or something like that. Maybe a principal polarization or something like that. But we don't have to think about that yet. We're just thinking of it as an abelian surface. Is it also true that if we included the complex torus, that there would be a rank 0 case? Is that right?
Yep.
Okay. But somehow we're just not bothering to include that. What?
It's more generic than generic, yeah.
Yes, yes. Sometimes it certainly is worth thinking about those, but at the moment we can just decide not to. So yeah, you've got this abelian surface, and it turns out it makes sense for it to have an endomorphism ring. It just makes sense. You can talk about endomorphisms, and you can add them, and you can multiply them. Right? Yeah.
Yeah.
So yeah, and that's a ring over the, yeah, it's just a ring. And but then you could like tensor it with various things. You can tensor with the rationals, or you could tensor with the reals, or with the complex numbers. It sounds to me like you're telling me that it might work if I just take this ring and I tensor it with the reals. And that after I tensor it with the reals, well, okay, so it's also, let's see. So we have this complex abelian surface. So it's, there's this two-dimensional complex vector space associated to it, which we can think of as the universal cover, or we can think of it as the tangent space at the identity, or something like that. Is that right?
Yep.
Those are natural equivalent. And I mean, that's got an endomorphism algebra, a complex endomorphism algebra.
Yep.
And we'd also think of the underlying real endomorphism algebra of that. So that's, let's see, I'm getting confused now. Let's see.
Well, the endomorphisms of the curve will map injectively into the endomorphisms of the complex.
Yes, okay.
They preserve the complex structure. There's not like complex conjugation, for example.
Right. So I think we're saying, there's this 2x2 matrices with complex entries, but we probably do want to think of that instead of thinking of it as a 4 complex dimensional algebra, we probably think of it as, I think we want to think of it as an 8 real dimensional algebra.
Certainly the Rosati involutions has a potential to be conjugate linear. So so to that extent, yeah. Maybe there's like some other reason why you want to think of it as real.
Well, yeah, let me try to say. So, I'm trying to think of this as this 8-dimensional real associative algebra. I'm trying to think of it as this ambient thing in which all our endomorphism rings of the abelian surfaces will naturally live, inside of which they will naturally live.
Yeah, I mean, they also live in the 4-dimensional complex algebra, but yep. I mean,
Am I saying that wrong? No, I guess you're right. Okay, I mean, right. I guess you're saying it right. Yeah. So let me think about what you're saying. All right, maybe I was being unnecessarily complicated. Let me think. So you're just saying, just think of these as complex things. Let me think about that for a minute.
yeah, no, that's good that you're saying all this stuff, because I think people do often take the endomorphism ring and tensor it with the rationals. And right now, I'm sort of wondering what, if anything, that buys you that you don't get when you just go up to the complexes.
Well, but it may very well buy you something, because for one thing, we have very limited goals here. Just calculate the rank, the Néron-Severi rank.
Yeah.
So that's less specific than actually calculating the Néron-Severi group. So
What do you mean? How does the group? You mean calculating the group up to more than isomorphism of groups?
Yeah.
Okay. Exactly.
I mean, yes.
Okay.
I mean, how it fits into this ambient thing.
Yep.
That's more specific knowledge than just knowing the rank, I think.
Mm-hmm.
Okay, but you're really telling me I should just think of this as a complex associative algebra. Is that right? Why did I not think about it that way?
I didn't ever think about it that way.
Say that again?
I didn't think of it that way myself, except in particular when we would always start talking about like the relationship of Minkowski spacetime to self-adjoint complex matrices. But there we were already doing self-adjoint ones, so you'd sort of like gone beyond the not using it.
All right, but okay. Well, a lot of things I'm very uncertain about here. So okay, so let me try thinking about this complex associative algebra. It's actually a star algebra, complex star algebra. Well, it gets the star algebra as soon as we have a polarization on the abelian surface.
Right.
I think.
Yeah, it does. Sometime we could, I don't know if we've ever really talked in detail about why that's true, but we don't need to now if you don't want to.
Yeah, I think we've probably each thought about it in a lot of detail, but
yeah. Okay, well.
So at some point I was guessing something analogous for the real algebra, but now it sounds like maybe you're trying to convince me that this works for the complex algebra, that the so now we've got the polarized abelian surface. We've got polarized complex abelian surface, and it has its endomorphism ring. And that endomorphism ring has a ring homomorphism to this associative star algebra, complex associative star algebra that we're talking about, right?
Mm-hmm.
And there's a ring homomorphism there. So we could take we can take that subset, that subring, and we can close it under real scalars. And under, well, just under multiplication. So we're going to take the, the hull of this ring, but the hull as a real associative algebra inside of this complex associative star algebra. It sounds like you're telling me that that will automatically be not just closed under real scalars, but it'll be closed under complex scalars as well. Is that one of the things you're telling me? Is that obvious?
No. No, it's not obvious.
I almost thought that's what you were trying to convince me of. I thought that's what you were trying to convince me of, because you're saying that. What were you saying?
No, I'm not saying that you can multiply an endomorphism by I and get a new endomorphism. I'm saying that any endomorphism commutes with multiplication by I on this tangent space.
Okay. So I think we were just getting, maybe it's just completely my fault. We're getting caught up in an ambiguity in what I meant by calling something real. So right, there's two places there that real is occurring. We're talking about like a real algebra of real endomorphisms, or a real algebra of complex endomorphisms, or a complex algebra of complex endomorphisms. And the other one presumably doesn't really make sense.
Well,
Let's do something funny. Right, so we are dealing with complex endomorphisms, but the algebras are real. That's what I was, okay. So that's what I actually had originally planned. And then somehow I was getting confused and thinking that you were telling me that these algebras are going to be complex algebras. But no, we are dealing with these real algebras.
Okay, yep.
And yeah, so we're taking the hull as real associative algebras inside this complex associative star algebra. And I also got the vague impression you were telling me that that would automatically be closed under the star operation as well. I mean, if not, we could perhaps, include that as well in what we're closing under, but.
I think it is. So, I mean, this gets back to like, what is the Rosati involution exactly? And I think you can.
Yeah, I mean, there was all that fine print in the definition of Rosati involution involving the rationals or something like that. But
yeah, so people often seem to define it after you've tensored with the rationals. But
yeah,
anyway, it would be good to sometime to see if you can define it just straight off the bat on the endomorphism ring. It's been a while since I've thought about that. I was very curious about that stuff for a while.
About which part of it? The what?
Whether you can define the Rosati involution directly on the endomorphism ring itself.
Yes,
So that is, which is
I didn't completely follow what you were doing when you were doing that, but it did sound very interesting. I probably should go back and reread.
I mean, the main reason why I was interested
Yep.
was just like trying to understand like what really is the Rosati involution. So usually like the more you get to know something, the less pre-processing you have to do to have it be there. And so tensoring with the rationals seemed like some kind of pre-processing that I would wish to avoid when trying to get to the bottom of the Rosati involution.
Oh, I certainly agree. It would be nice if we could do that. But I got the vague impression that you were trying something else, which it sounded interesting, but confused me. It sounded like you were trying to, maybe I totally misunderstood. I thought you were trying to somehow define something related to I mean, to me, the involution comes from the unitary structure. Yeah, from the polarization. I thought you were trying to do something that was polarization independent.
Yeah, I did do that. I think, yeah, so there's a polarization independent version of the Rosati involution where you don't, yeah, well, I mean, I could go into it again, but I think I understand how to do that.
I should ask you about that later and or read about that later, but I'm not.
That's sort of important for, that's sort of nice if you wanted to like get the complex surfaces without that aren't abelian into the picture so that you can even talk about the Rosati involution and see if the Néron-Severi group still can be defined using the Rosati involution in that case.
That's interesting. I'll have to think about that. But all right. There's probably things I'm forgetting to say as we're going along here. But so I think the vague impression I got is that you've got this complex associative star algebra in it. You've got this complex associative star algebra, just a matrix algebra, 2x2 matrices. And you could start off just trying to classify perhaps up to conjugacy or something like that. Classify the sub things of that. When I say sub things, I mean in this case, not that it should be the same kind of thing, but that it should be a real associative algebra, and I think closer to the star operation. And you could try to classify all of those, and maybe that is really more or less equivalent to this classification that you're doing. Is that equivalent to what you did? Did you like classify the real associative star subalgebras of the 2x2 complex matrices up to the hopefully obvious kind of conjugacy, and then interpret those classes as being these classes of abelian surfaces? That's not what you did?
No. Sounds fun, but what I did was try. Are
you sure you weren't secretly doing
that? Depends how secretly.
From yourself, yes.
So secretly that I would say no, I'm not doing it.
Right. Okay. So go ahead.
So what I thought I was doing was thinking about the endomorphism rings sitting inside as sub rings of that 2x2 matrix algebra. For starting from an abelian surface,
yes,
try to sort of guess what its endomorphism ring was. Think of it as like sitting inside this 2x2 matrix algebra.
Yes.
And then assume that the Rosati involution was just the could be thought of as just the usual conjugate transpose on the 2x2 matrix algebra. and then look at this, my guess is to the subring and figure out what the self-adjoint elements were. So the elements fixed under this Rosati involution. That's what I did.
I still think that that's almost the same thing as what I said.
Well,
I mean,
maybe it is. Yeah, maybe it is.
Yeah. I mean, it might not be obvious that all of the classes of the sub things that occur might not be obvious that all of those actually come from abelian surfaces. I think it might be true that they all come from abelian surfaces. And
well, we can.
I mean, how do you even know? See, I'm still suspicious that you had to secretly be doing something like like what I said, because otherwise, how are you clever enough to know that, you know, these different criteria that you're using about the complex multiplication and the Cartesian square, the Cartesian product, how did you know that that was going to control what algebra you were getting?
It just that I know that when you get these extra niceness features, I can see more ways to get a hold of endomorphisms. And I'm not at all proving that I'm getting all the whole endomorphism ring, but I can just see. So, I mean, I could be much more persuasive if we did an example, but if you give me one of these kinds of curves, I could tell you a bunch of endomorphisms. That's, to me, it was plausibly all the whole endomorphism ring. And then I could think of how that ring would plausibly sit in the 2x2 matrices, very plausibly. And then I could just figure out what the self-adjoint part was, and that's supposed to be.
All right, so if I understand what you're saying, you're just suggesting that those criteria are sort of more or less obviously connected with what the endomorphism ring is going to be. That, you know, when you have a Cartesian product, that helps you get some endomorphisms. When you have a Cartesian square, that helps you get some more. I mean, of course, complex multiplication, it helps you get some more.
Yeah, exactly.
Okay. So,
yeah, so I was just assuming that there's like no sneaky extra endomorphisms beyond what you can get out of that stuff.
Okay. So, right now, so now I'm idly imagining whether the finer classification that you used in case 2 might actually fit with something that I was going to try here, which is, you know, I'd really like to know the Néron-Severi rank, but I'd also like to know the rank of this whole real star algebra.
Yeah.
And
yeah, that's
and then that should decompose as a sum of a self-adjoint rank and a skew-adjoint rank.
right. Yeah, and so it's not giving away too much to say that in that case 2 there, list the cases by number. In case 2, we're gonna like see different things happening.
All right, so let's try that. So okay, let's think about that for a moment. Let's think about case 2 for a moment. So, yeah, don't quite give away the answers yet. So it sounds like you're saying, let me think. Cartesian product. So these, okay. So these are all roughly of diagonal flavor. And
these endomorphisms.
Say it again?
These endomorphisms, that's what you mean by these, right? Yeah.
I was actually thinking of the subalgebras as being diagonal in flavor, but
right, yeah.
Yes, that's because the endomorphisms are, yes. So again, no, the answer is by staring in the face of it. Just don't tell me right away. So it sounds like you're saying, you know, we have these diagonal matrices, so 2 entries on the diagonal, and it sounds like it's, in some sense, the 3 cases are where, in some sense, both those entries are complex, or one of them is complex and one of them is real. or they're both real.
Uh-huh.
And in all of those cases, right, so this is going to be a commutative endomorphism, right? And you know, so the reals as a real star algebra, and the complex numbers is a complex as a real star algebra. Reals and complexes, both of them as real star algebras. The complexes have more of the skew-adjoint stuff, but they don't have any more of the self-adjoint stuff.
Right.
So
That's right. That's how you don't see this in the Néron-Severi group. The distinction.
So sounds like you're saying there's 2 plus 0 and 2 plus 1 and 2 plus 2.
Yep.
Where now I'm writing these sums of just the self-adjoint part and the skew-adjoint part. And I'm also vaguely thinking that they're right. There is probably some sort of conceptual interpretation of the skew-adjoint part. It's like measuring some symmetry group or something like that. So, okay, so let's see. So the 1 sounds like you're telling me that that is 1 plus 0.
Uh-huh.
And
right.
The Cartesian square. Okay. Let me think about the Cartesian square of the generic thing. So that should be like everything is real. Well, but what do I mean by that? Let me think. Let me think what you're saying. What are we trying to say here? What are you saying? Okay. Let me think.
I know.
It's not. Yeah. What?
I'm waiting for you to write down something in red.
It sounds like you're okay. I'm going to write it down, but don't criticize it. Right? Don't say anything.
Okay.
I guess
My
you're allowed to have
doesn't mean it. I'm just laughing just for fun. Not to,
yes, you're allowed to have a facial expression, I think,
yeah,
but you're not allowed to
okay.
say that. This is not based on thinking it through. This is based on, you know, some silly thing. It sounds like you're telling me that it should be 3 plus 1, but now I have to try to come up with a reason why it actually should be 3 plus 1. And maybe it isn't 3 plus 1, but let's see. So 3 is supposed to be right. Okay, and this 4, well, what is this? Let's see. Let me get rid of that. How did that get there? Okay. Yeah, I don't know what the 4 is going to be. Let's see. 3, let's see. It almost sounds like it's going to be 4 plus, I don't know. Maybe it's 4 plus 4. I don't know. Let me think about the. Three plus, okay, can I get the 3 plus 1 to make sense? Let's see, so 3, well, so let me think about the real, you know, 2 by 2 matrices with real entries.
Yep.
And let me think about what the skew symmetric ones are like and the symmetric ones. Oh, so maybe that does Makes sense. Yeah. Okay. Maybe that's what it is. Maybe the 3 is the symmetric ones, and the 1 is the skew symmetric ones.
Yep. I'm allowed to agree when I
Yes.
you're right. Okay, I have to like shut up until you're right. So, so yeah.
All right. So the 4. So yeah, I know this is ridiculous to solve, but it's immeasurably helping me. So let's see. Okay, so there it sounds like you're saying it's the 2 by 2 complex matrices. And yeah, so it is just 4 plus 4. I think. Sorry. And
I mean, I'm going to come out and say, yes, I think that's right too.
sure. Yes. Now you're right. Now you're allowed to say it.
Yeah, so you can look at 2 by 2 complex matrices and look at the self-adjoints and the skew-adjoints. And yeah. So the big thing you're doing that I wasn't doing, which seems like, to me, it seems like extra work, although ultimately it's maybe less work, is that I was actually thinking not about the reals, but actually thinking about like the number rings. Well, yeah, the number rings that are giving these elliptic curves. So I was looking at lattices inside the real vector spaces that you're talking about. But I mean, this is simpler, but you have to like,
there's some trade-off.
Yeah, you have to somehow believe that it's okay to just go up to the real level. And I think it is,
right.
Yeah.
But it almost sounded like, right. It almost sounded like you were conjecturing, or implicit in what you were doing was a conjecture that this would work, and that this would work for abelian n-folds, abelian varieties in arbitrary dimension or something like that. If you classify.
Yeah, I wasn't thinking at all about this real stuff the way that you're doing. I mean,
I still think you were.
Okay, well, okay, fine. But I like you thought I was thinking about the complex numbers.
No, but you almost even said you were. You mentioned how the whole Brouwer thing simplifies from the rationals to the reals. You were really hinting that we wanted to exploit that, I think. Am I still wrong in thinking that we can exploit that in this way?
I think that's probably ultimately what we're doing. But now what I'm really confused by is like,
yeah,
what, like, I don't know what the classification of division algebras, of simple algebras over the rationals is well enough to like to know like what it is that we're losing out on when we go to the reals. I mean, I know, well, I think I know a little bit about it, and I think in some sense we're like losing out on a lot, just in the terms of the classification of algebras.
Going from the rationals to the real.
I think, yeah, I think so.
Yeah, we should be using, yeah, but that's supposed to be good. I mean, if we're
right,
we're just thinking about the rank here, but yes, go ahead.
Right. So, I mean, I want to understand that better. I was studying this Noether Hasse-Brouwer collaboration where they were like figuring that stuff out.
Yes.
But somehow I don't have a really solid grasp of it. And so one thing I'd like to know sometimes is like,
by the way, how much younger was Brouwer than Noether?
I don't really know.
Okay, never mind. Go ahead.
Yeah.
I mean, but that enters into, the interpersonal interplay between them.
Yeah.
But,
I guess I gave you some of those quotes or something. I don't know.
Yeah.
Or maybe I just alluded to just sort of sound like, very good, you're doing pretty good. But anyway, so like what I'm really curious about now, which should be lurking in this big fat book on complex abelian varieties, is like, could we like use the more fine-grained rational classification to learn some more stuff about abelian varieties?
Sure,
But anyway,
sure.
we're not doing that now, but
Yeah, no, what, not, no, that definitely not, but definitely that may be worthwhile later. So let me just comment, going back to this silly chart here, the 3 plus 1, the 1 is the dimension of a Lie algebra. Let me just name that Lie algebra, because it's what I might call SO2 in the 3 plus 1. And in the, maybe I should say O2. I guess I should say O2 rather than SO2. Is that right? Because now I look at the next one and I see 4 plus 4, and the second 4 is the dimension of a Lie algebra, and that's evidently the Lie algebra U2.
uh-huh.
Right?
Yeah.
Yeah, and then those other ones are probably something obvious. Yeah, those zeros and 1 and 2s. Okay.
One of them, the most fun one would be like O1 plus O1. The most
Yes,
novel
yes.
one.
In the 2 plus 2, the
Yeah.
second 2 is O1
Yeah.
plus O1. Okay, so let me think about another case here that I don't think is listed. I don't think it quite fits into your case here. Let's try to think about the 5th cyclotomic field and how that gives allegedly an abelian surface with complex multiplication by the 5th cyclotomic field. So in terms of a sublattice of the complex numbers squared, did we say what it was? So how did that work? I guess the way it worked was you think of that as a ring. You think of the complex numbers as a ring. Complex numbers squared as a ring. That a ring. And inside of that ring, you've got the initial ring, which is the integers, and then you just put in one more generator to obtain a subring. And that one more generator is 1 to the 1/5, comma 1 to the 2/5. I'm not sure I remember all the details of this way. It's very easy and nice to understand, but I'm sort of repeating things I think I said in the email.
Yep. I remember that stuff. Yep.
And that that generates a subring, which is a lattice, if we do it right. A lattice in the complex number squared. And I'm pretty sure it's the right kind of lattice, right? There probably is, right? It's obviously a complex torus, but I think it's pretty obviously not just a complex torus, but an abelian surface. But in any case, that's what we'd like to clarify. We'd like to see the Néron-Severi group of this complex torus. So let me try to think out loud very ad hoc, very carelessly about this example. Do you have any idea so far about what's going to happen in terms of this real star algebra that we're going to get from this example?
No, I want to know what the endomorphisms ring is.
Well, I know it's pretty damn close to being the 5th cyclotomic ring itself. Now, I'm a little bit confused. There might be a little tiny bit more than that, which might be the Galois symmetry. But actually, which Galois symmetry do I mean? But right, so what am I trying to say? I mean, I think it's going to be the 5th cyclotomic ring itself. That makes sense, right? I mean, if it's got complex multiplication, I mean, again, it may have this 1 or 2 extra Galois automorphisms or something, which somehow those might somehow fit into the endomorphism ring. But most of the endomorphism ring is that, I think. And I mean, to me, that sounds a lot like rank 2 again. What am I trying to say? Right? It's going to be this is a commutative ring. Now, if there may be an extra Galois automorphism or 2 that doesn't commute with everything, but this bulk of it all commutes with it. So that's got to be, that's one of those diagonal things, I think. And it's going to be, like the complex numbers itself.
So you mean it's a subring of the complex, a lattice that's a subring of the complex numbers as a
Yeah.
ring.
But in particular, when you close it up into real scalars, you're gonna get this thing that is just like the complex diagonal 2x2 matrices. I think. Complex diagonal 2x2 matrices. Yeah, and then the one extra Galois morphism is somehow conjugating those 2 diagonal entries or something like that, I think. But I don't want to worry about that. But so yeah, I mean, that's right. That sounds like the 2+2 case again, right?
2+2? I thought you said the automorphisms were like a subring of the complex numbers. So it sounds like a 1+1.
No, I didn't mean to say that. I meant to say it's more like the. What am I trying to say? I mean, right. Anytime you have a commutative ring, it acts by multiplication operators on itself, and if it's over the complex numbers, right? A commutative complex associative algebra, commutative and associative complex algebra. It's just like particularly if it's this semi-simple thing, which perhaps comes from the star structure or something like that. It's going to be, just like it's going to be the complex numbers to the nth power as a commutative algebra. And so it's just the diagonal multiplication operators. We thought as diagonal operators.
I thought that the endomorphisms of this. I'm confused.
Saying something stupid? Go ahead. Yeah.
I don't know. I don't know. I'm trying to. What is this lattice that in C2 that you're modding out by to get the abelian variety? So you say this lattice is the subring, the ring generated by 1 to the 1/5, 1 to the 2/5.
Yes, that's right.
So then there's also like.
Which is the 5th cyclotomic integer. That ring is the 5th cyclotomic integer.
Right, but okay, so it sounds like you're trying to say that ring is fat enough so that when you tensor it with the reals, you get C².
Yes.
For some reason, okay, so I was.
I mean, you know, the fifth cyclotomic integers as a ring is, you know, rank 4. The fifth cyclotomic polynomial is a 4th degree polynomial. It's just, you know, x to the 4th plus x cubed plus x squared plus x to the 1 plus 1.
Yep.
So yes, when you tensor with the reals, you're getting something 4 real dimensional inside of this commutative semi-simple thing, which is the diagonal 2x2 complex matrices. So it's that whole thing.
I'm confused because like this fifth cyclotomic integers are like a subring of the, they're already a subring of the complex numbers if you want.
Ah, but only in a very dusty way. See, okay.
Yeah, that's probably part of what I was getting. I was
Yeah,
forgetting that. I don't know how much that, I don't know if that.
I mean, this, yeah. I mean, this is partially a demonstration that there's a whole fascinating subject of complex multiplication, which, you know, in the past, I've tried to reinvent it for myself. Recently, with Todd and some other people, I've been actually reading about it. But you haven't been doing that yet, so it's not surprising if you haven't seen a lot of this yet. But yeah, so there's right. I mean, there's this stuff that you probably haven't thought about yet about what you were just talking about how this, you know, like you say, as a subring of the complex numbers, it's proper dense thing. But sort of the whole point is that, well, you get a cleaner picture if you know, don't just take the generator to a single primitive fifth root of unity, take it to all possible fifth roots of unity, except you only have to take it to half of them because of, well, there's some good reason for it. But yeah. So I mean, yeah, it's not as bad as you might have been worried. It's gonna work. I mean, at some point we could really go back to really draw these very explicit pictures of the fifth cyclotomic field. Well, I mean, how do you draw pictures of this thing? But I mean, it's sort of, you know, 4-dimensional over the rationals or 4-dimensional over the reals or something like that. But it's got this golden field in it, you know, the golden ratio, and that's 2 dimensions over the rationals or the reals or something like that. And you know, you just complexify that to get the whole fifth cyclotomic field. So right, okay. So okay, so let me take a stupid guess here. So we're supposed to take the self-adjoint things inside of this allegedly 4-dimensional commutative algebra that's like the 4 real dimensional commutative algebra that's like the complex diagonal 2x2 matrices. So, and then we separate into self-adjoint and skew-adjoint. So it sounds to me, am I screwing up here? It sounds to me like these self-adjoint things are actually going to be the golden integers itself. Is that right? What am I trying to say? Is that the wrong involution? Am I applying the wrong involution there? What I mean, the golden integers is sort of like the real part of the fifth cyclotomic integers. And Yeah, and that's right. That's what we kind of do. We take the real part, right? If in the commutative case, we're really just taking the real part of these scalars, I think. So unless I'm screwing up, it looks to me like.
So you're getting 2 plus 2. Is that as your?
Yes, that's what I seem to be getting. I mean, I'm being very sloppy about it, but that's what I seem to be getting. It sounds like I'm claiming, maybe, there's a lot of details to check here, but it sounds like I'm claiming that we can actually identify the Néron-Severi group in that case with the golden integers themselves. And that confuses me because, right, I'm so used to this idea that we have, the space-time and the spinors, and they're very separate things. They're very nice representations of the same group, but they're very different representations. But here it almost sounds like I'm claiming that there's this important part of the spinors that's actually an important part of the space-time. Is that right? What am I trying to say? I mean, the space-time, the spinors. So the fifth cyclotomic integers would be the spinors. But inside of that, there's this golden integers. So that's like part of the spinors, but then I'm seem to be claiming that that's also part of the space-time because it's the Néron-Severi group. So am I screwing up there? Does that make any sense? Is this all too confusing to disentangle it right at the moment?
It's confusing, but that extra twist is extra confusing.
Yeah. I mean, we don't have to worry about it. We don't have to worry about it right now if you don't want to. But go ahead, yeah?
I mean, it sounds like some of the confusingness should be something you should be able to state just using complex numbers and real numbers and not this golden
that's right.
stuff. So if you could restate it that way, I would probably be able to figure it out. So I mean, the space-time.
Right. Exactly, yes.
Okay.
Exactly, but I think that gives us the excuse not to worry about it right now because what you just asked me to do, it seems like I'm too lazy to do that right now. So I should think about that for later.
Okay. I'll just make a wild guess.
Go ahead. Yes, go ahead. I mean, it does remind me about all that integral spinor stuff that you told me about, but that seemed more like a quadratic thing than. Go ahead.
Well, yeah, there's this quadratic. So I mean, there's this thing that like any spinor gives you a light-like vector. It's which you can think of as.
Again, is that a quadratic thing or is that a linear thing?
Yeah, it depends on it quadratically. Yeah.
Depends on quadratic.
So that's the only thing I know about how you can like see a spinor as giving you a vector. It's Penrose called it this flagpole business where you think.
Say it again. Who calls it that? What?
Penrose calls this flagpole description of spinors, where you think of a spinor as
that really is Penrose, because somehow I always associate that with that other guy, Wheeler, Feynman's collaborator or somebody like that.
Oh, Penrose definitely talked about it. Maybe you got it from Wheeler. I don't know. Yeah.
Or I could be completely mixed up. Maybe it is Penrose.
So you think of a spinor as like a light-like vector together with a little circular amount of extra.
But really, but in the flagpole business, there's really some quadratic annoyance going on.
Yeah. So you're linearly picking out a vector out of a spinor?
Well, it sounds a little bit suspicious, but it almost sounds like that's what I'm claiming. That there could somehow be enough extra structure going on that allows us to do that. I'm not quite sure. It sounds like I want that to be happening, but I'll have to think about that more. But I think, again, I still think this is a really good example to think about this fifth cyclotomic stuff. Now, there's also the Boltzmann curve, or how do you pronounce it? The Boltzmann curve. Which, does that fit or not fit into the classification here anywhere? Is there anything obvious we can say about it?
You mean surface, by the way?
You're trying to confuse it. So
Oh, is it a curve? Oh, what do you? So it's a
yeah,
curve, and then
right. I think there's the Boltzmann curve, which is genus 2, and therefore its Jacobian
okay, that's the surface. Okay, yeah,
is an abelian surface.
yeah, okay. Yeah, I
And,
haven't thought about
and
this.
of course, this is really annoying. This is really combined with in a really annoying way with the fact that if you look it up in Wikipedia, I think it says Boltzmann surface, but they mean the underlying real surface of the complex Boltzmann curve.
Okay.
So yeah, there's this complex abelian surface, which is the Jacobian of the complex Boltzmann curve.
Mm-hmm.
And yeah, so one of the things I'm doing is I'm asking you to try to tell me everything you can everything you can figure out about where that does or doesn't fit into our classification, how you might have to stretch our classification to include that example. For one thing, how far did we ever get in deciding what is this abelian surface directly? Instead of saying that it's the Jacobian of the Boltzmann curve, what is this abelian surface? And you know, so then you could try to say it in terms of, oh, it's some familiar lattice, except that I get confused about how you're supposed to distinguish lattices up to what sort of equivalence relation. I'm used to distinguishing them up to Euclidean equivalence or something like that, but here we're distinguishing them up to unitary equivalence or something like that.
Right.
And you know, so when you start talking about D4 or whatever, I thought those were, you know, names in the game of classifying lattices up to Euclidean equivalence or something like that. Or am I confused? I don't know. But I mean, even if they are, you had some sort of guesses about how it might fit in anyway. I mean, did you have any guesses about, you know, some very concrete way to describe what this lattice is that corresponds to the Jacobian lattice of the Boltzmann curve? And possibly did you come up with a guess just on the basis of, you know, symmetry considerations or something like that? Have you got a lattice that seems to have the right kind of lattice symmetry, unitary lattice symmetry, whatever it is? Yeah.
There is a lattice that I was thinking about that I liked, that I don't know if I ever claimed it was connected to the Boltzmann curve, but it has.
Talking about the quaternions, is that right?
Yeah, so just like this Hurwitz integral quaternions.
Hurwitz integral quaternions.
So if you think of the quaternions as c squared in a certain obvious way, 1 plus I, j plus k.
Yes.
Then this lattice is preserved by multiplication by I. So it's a kind of lattice that you could mod out by. You could take c squared, mod out by this lattice, and you'd get a complex surface. In fact, a complex torus, but in fact, it would just naturally have a Kähler structure. And if you expand or shrink the lattice correctly, it would be like this integral Kähler structure. So I think that you get some nice abelian surface here with whose symmetry, whose endomorphisms should include. So multiplication by I is something you can do on the left in the quaternions, and then that will commute with all multiplications by quaternions on the right. And so here, multiplication by all the quaternions in your integral quaternions acting on the right should be endomorphisms of this surface. So this should be a nice case, unless I'm really confused. This could be like a case where when you realify it, tensor the reals the way that you like to do.
Yeah.
Your endomorphism ring would turn into the endomorphism algebra, which would be the quaternions, or at least contain the quaternions. Maybe you get more, but maybe there's also endomorphisms where you act on the left by complex, by like Gaussian or something like that. but anyway, so this seemed like an interestingly symmetrical abelian surface.
Yes.
Now let's see. Is there any reason to think that that's connected to the Boltzmann? So the curve, so the symmetries of the Boltzmann curve.
I mean, yeah, if the symmetries come out anywhere near similar, then that would be possibly a big clue. I mean, we used to have some vague idea what the symmetries of the Boltzmann curve were.
Do you remember? I can't remember.
Well, it was well, it was very octahedral-ish, right? But it had, you know,
Right.
some cover. I think you told me it was something, right? There's slightly different versions of the endomorphism group, depending on what you're preserving. But there was something about a double cover of the icosahedral group, which wasn't the most famous double cover. That's what I think you told me.
Okay, octahedral group, you mean? But yeah.
What did I say?
Icosahedral.
I meant to say octahedral. Yes.
Yeah, right.
So it's,
oh, okay, so I said that, huh? Okay, that's.
Well, and also you may have gotten that just by reading something from.
I probably was
Wikipedia
just, I was probably just reading Wikipedia.
I mean, we may have had to, you know, massage it to slightly reinterpret what they said, but yeah.
Okay, so that sounds like it's a little bit different because the Hurwitz integral quaternions have symmetries that are the as a ring. They have symmetries. Wait a minute. They're connected to the binary octahedral group, but that's like the ordinary binary octahedral group.
Wow. But still,
yeah,
I don't know, maybe we can somehow get that to work or something like that. If they're both, okay, so, okay, it sounds like you're at least saying that they both have something to do with the octahedron or something like that. Possibly not enough to be actually the same curves, the same abelian surfaces. But it's slightly suspicious if they both are related to octahedron.
Yep, yeah, it'd be definitely good to think about.
All right, so let me raise some vague general issue here, which is, so partially what we've been fooling around with here is, you know, allegedly just motivated by trying to understand what a Néron-Severi group is and so forth. We've sort of tried to write down very informally, very roughly, some classification of abelian surfaces. I mean, it wasn't intentionally that way, but it ended up being sort of like classifying them according to how generic versus how special they are. And we could, you know, presumably do this in a much more careful way, and we could do it for abelian varieties of some higher dimension.
Mm-hmm.
And, but then on the other hand, you could also imagine there could be a number of different variations on how a game like this might work. And by a game like this, I mean classifying abelian varieties of some given dimension according to sort of how generic they are. So like, I mean, one slightly different, maybe very different criterion for what you mean by how generic they are, how generic an abelian variety is. You could just mean something like how stacky it is as a point in the moduli stack of, let's say, principally polarized abelian varieties of whatever that dimension is. And so like how closely would that compare to the classification that we're attempting here? I mean, the generic ones, those are very unstacky.
So one interesting thing is the stackiness seems to be connected to automorphisms, whereas here we're really focusing a lot on endomorphisms.
Right. That's one of the issues here. But it almost seems like the endomorphisms are kind of hidden automorphisms in some sense or something. I don't know. I don't know what I mean by that, but.
Well, it may be connected to this isogeny baloney. So a lot of times people think of like a different category of.
Yeah, that's a possibility. Yeah.
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 So like when you have complex multiplication, it's not always acting as an automorphism, except, you know, in those famous, like for elliptic curves, just like only in the Gaussian and Eisenstein, you see it as an automorphism in the category of in the obvious category of elliptic curves. But isn't it true that, like, yeah, I think like even when it's just like a complex multiplication of in a different, not one of those cases, it's still an isogeny. So it's like it's an automorphism up to covers.
Sorry, you're talking about abelian varieties in general, or abelian
I'm just
surfaces?
focusing on elliptic curves
Oh,
for concreteness sake, for example's sake. It's supposed to be a general point, but like,
yes, but yes. So yes, let's say elliptic curves. Yes.
so then, like, if you have one with complex multiplication,
Yeah.
typically that complex multiplication is not an automorphism of the elliptic curve in the sort of naive, obvious sense.
Yes.
But I think it's still, I'm really confused. I think it's still an isogeny, meaning
Yeah,
that, like,
yeah, no, that sounds vaguely on the right track to me.
So now I'm all of a sudden wondering if, like, your sense in which like endomorphisms might be like hidden automorphisms. I mean, there's some endomorphisms that there's no way to rescue them, like multiplication by 0 or something like that. But there are a bunch of endomorphisms that are sort of.
Yes, I think that's what you're saying is exactly what I was vaguely hinting at. Very, very good.
Okay, yeah.
And partially because I've gotten that impression from some other people who have heard talk about stuff like this. But what was I going to say?
So anyway,
go ahead.
So one last thing, I mean, maybe you don't
Yes.
know, but I'm just wondering if, like, do people ever look at like moduli stacks of elliptic curves or abelian varieties where they
up to isogeny?
Isogeny, yeah. So it's like,
yeah, that's exactly the same thing I was about to ask. And I was wondering, it almost, I mean, I was afraid that if you did that, you know, you might get something, you know, that coarsening process, you know, passing from isomorphism to isogeny. I was worried that would be in some ways an ugly coarsening process. I was afraid that, you know, an elliptic curve might have other elliptic curves infinitely near to it that it's isogynous to, or something like that. But I don't know.
Doesn't sound right to me, but anyway, yeah. That fear doesn't sound correct to me, but.
I don't know. I remember, what if you unwrap by, you know, 200 times and then rewrap by 201 times?
Yeah, okay. Yeah, maybe you're right. Yeah, maybe you're right.
I have no idea. I have no idea. But anyway, that's a fun question too. So okay, but let me keep going with a vague general question I was trying to aim at here, which is, what am I trying to say? Well, so like I said, we have, you know, possibly different variations on this game or these games, but we have the vague idea of trying to classify these abelian varieties up to something like how degenerate they are. And that's somehow related perhaps to how symmetric they are, or perhaps how much hidden symmetry they have. I don't know, something like that. But the vague theme I was going to ask about here was that in certain very simple cases, we have some very nice relationship between, well, let's go to the case of elliptic curves. So, you know, the very basic case of elliptic curves. And the very basic, so right at the moment, I want to focus on classifying elliptic curves just according to how stacked they are. So we're not, you know, considering the arbitrary complex multiplication to be special. Well, we're only considering the Gaussian and the Eisenstein ones to be special, because those actually globally or whatever actually affect the automorphism group. What's that other fancy word? The isotropy group? I don't know. But so So in that case of elliptic curves, we have this very nice photogenic moduli stack of elliptic curves. And we can consider more general modular curves, which are unwrappings, uncoverings of this moduli stack. And this covering process, this unwrapping process, is in some sense completely controlled by keeping track of the elliptic curves with some vague informal sense. It's completely controlled by keeping track of what happens at these stacking elliptic curves. Well, keeping track of what happens with the Gaussian, the Eisensteinian, and the idealized cusp point or something like that, right? So, I mean, you think of a modular curve as some sort of combinatorial object. It's like a, right, you've got this Coxeter group. What does the Coxeter diagram look like? Where did I put my pen? Did I lose the pen? Okay, I've got the pen here. What does the Coxeter diagram look like? Let's see, I always get confused, which end is which. So the Gaussian must be the thing in the middle or something like that, right? That's the...
I don't even know. Well, how do you know that? How do you remember that?
Because it's very four-ish or something like that. So what am I trying to say? That the Coxeter diagram that you get by erasing the blue dot, that's the things that stabilize a Gaussian or something like that. Is just a separated Coxeter diagram, just an isolated green point and an isolated red point. And that's just like a Klein 4 or something like that. And that's like this. Am I saying that's right?
Sounds convincing to me, yeah.
Yeah, I think that's right.
Okay.
I say Klein 4. I'm not going to worry about it, but yeah, it's something like that. So one of these edges is a vanilla edge that just has the label, implicit label 3 on it, and the other one has the explicit label infinity on it. I'm trying to figure out, so like, what is it? One is these, the destabilizer of a Eisensteinian thing versus the destabilizer of a cusp. I guess it's like, these are the cusps, so maybe it's an infinity. I mean, in some sense, it doesn't matter. That's, you know, one of them has an infinity and one of them, but I just can't remember, you know, whether the green now is the cusps or something like that. But I mean,
seems like the green is the infinity. If you remove it, then you're left with the 3, and that sounds.
Yeah, right. Let's just make a brief attempt to draw the Coxeter tiling. So what does it look like? I mean, it looks like triangles. But then these triangles get barycentrically subdivided. So obviously the blues are like edge barycenter. Is that blue? That doesn't look blue to me.
Oh.
Something like that. And then this says what? That a red, yeah, rotating around a red should be infinity. So that sounds like the cusps are red. Is that right? So sorry, cusp should be red, so it's like this. And then the green should somehow be there. Sorry, I keep on touching the wrong thing. So it's green, okay. So it's like there and there, there and there, and something like that. Yeah, well, something like that. And then, you know, you can put in the barycentric subdivision as well. So it's like, what? How does that go? It's something like, what is it, like that? That's the way it goes?
Yeah.
And like that. And like this. And then, how else does it go? Let's see, that's it. Okay, write something like red, green, blue, and then something else. I don't know. Et cetera, that's it. Something like that. And so this is completely unwrapped. And you can wrap this up in various ways. And it's, you know, the you know, some nice subgroup of this Coxeter group is becoming the stabilizer subgroup or something like that. And you're getting all these modular curves. But in some sense, the whole combinatorics of these modular curves is controlled by just keeping track of the blues and the reds and the greens. Again, the Gausses and the cusps and the Eisensteins, or maybe it's the Eisensteins and the cusps, but whatever. So and you know, the sense in which it's controlled by that is just that, you know, you just have to draw this little triangle complex where all the vertexes are blue and red and green. Sorry, blue and yeah, blue and red and green. And that's this picture of the modular curve. And it's, you know, it knows all, that combinatorial information is all you need to know about the modular curve. And right, so I'm imagining to what extent can we play a game something like this with other kinds of modular varieties. So for example, you know, the modular varieties of abelian surfaces with some kind of extra structure. So these modular curves, those are moduli stacks of elliptic curves with extra structure. And the extra structure is some kind of lattice framing or partial lattice framing. And you know, so for example, for these moduli stacks of abelian surfaces with extra structure, we're getting these Siegel modular varieties or something like that. And to what extent is there something analogous to this for those, you know, we have this combinatorial way of thinking about modular curves. To what extent is there an analogous story, analogous sort of combinatorial story about thinking about the Siegel modular varieties of abelian surfaces with extra structure, or principally polarized abelian surfaces with extra structure? And, you know, to the extent that there is, it sounds like it might have something to do with keeping track of all these different genericity or degenericity levels of abelian surfaces. Now, it's obviously much trickier than the elliptic curve case, but you know, there must be a lot of people who know a lot about this. But I don't think, for example, I don't think it's going to be just a Coxeter group that's controlling everything. I'm not even sure about that, but
yeah,
I mean,
I don't know. Yeah.
But the general question I'm raising, you're getting a sense of the general question I'm raising here. You know, like, you know, right? I mean, you could try to say something like, you know, take the moduli stack of principally, you know, the Siegel moduli space, sort of the Siegel modular variety of completely unadorned, principally polarized complex abelian surfaces. You take that moduli stack, but then you could perhaps point to a particular one of our degeneracy classes or something like that and say, let's unwrap by a factor of 2 or a factor of 3 or something on that little, I mean, so I don't know to what extent this is, but like, I mean, the product ones, those form, right? So we've got a 3-dimensional moduli stack now, right? 3 complex dimensional moduli stack. And the Cartesian product things, those form like a 2-dimensional substack, right? I mean, I'm taking vague guesses here, but it sounds very plausible.
Sounds right, yeah.
So that sounds like, you know, codimension 1. So it sounds like something you could unwrap around. So, you know, is there some Siegel modular variety that you get where the instructions are basically just to unwrap n times around that stratum or something like that? And are there all sorts of other things that you can do to keep track of all the Siegel modular varieties for this situation? So I'm interested in this, and I've gotten some very slight hints about, you know, where people have thought about this kind of thing. I have very little idea as to what the answers are, but I have some very slight hints about where people have thought about this kind of thing. So
yeah, I'd like to know what's the analog of Gaussian, Eisenstein, cusp. Like, what are the things, the cool places in the
I mean, right, again, I mean,
so there's some sub varieties now, not just points, you're saying.
Yeah, I mean, right, I mean, again, I have the feeling that the codimension 1 things might be very important, but the only real codimension 1 thing I see here is the products. But also, how close have we come? How hard have we tried, and how close have we actually come to like giving a complete account of the different degeneracy levels of complex abelian surfaces, and of course that includes, of course, actually deciding what counts as a different degeneracy level.
Yeah, I'm interested in exploring the ones where the automorphism groups might be subgroups of SU2, interesting subgroups of SU2, that is quaternionic multiplications, discrete, giving you discrete subgroups of SU2. I don't know if I'm, so we were talking about.
Isn't that the general case? Am I saying that, you know, once you're preserving the polarization, I thought we convinced ourselves at one point that that is exactly kind of the situation that you're dealing with, or almost exactly the situation that you're dealing with. That, right? That SU2 is right. I mean, we've got this Minkowski group, but as soon as you're preserving an observer's,
yeah, when I say
you're preserving an SU2 or a U2, an S.
Yeah.
What am I trying to say? Whatever.
Yeah, I think, yeah, an SO3 or an SU2.
An SO3, yeah, something like that.
So, yeah, so what I meant was, I didn't say it very clearly. What I meant was like,
yeah,
subgroups of SU2 that were
in the Mackay classification, or what?
Yeah, well, yeah, the pretty big ones. So I mean, so there's not that many of them, but like the icosahedral, octahedral, and tetrahedral ones, as opposed to the ones that we've been talking about, which are like in your last notebook page. Can you go back to that in that last page there? You had like different Lie algebras. Let's see. Yeah, does that even make sense? Are those?
Yeah, I'm not sure. Let's see.
Is that completely irrelevant? Let's see those Lie algebras there. So
no, you're probably right. Something about how we're looking for finite subgroups in those Lie groups corresponding to those Lie algebras, or something like that.
I'm confused if that's.
I mean, like the 4 has one, it's U2 rather than SU2, but maybe that one extra dimension is very non-compact and it's not going to give you any finite subgroup. What are you going to say?
Yeah,
I said something strange there. I mean, U2 is still very compact.
Yeah, I was not even worrying about that. I was just like trying to think about whether these Lie algebras here that we're seeing are at all
relevant?
At all relevant to like the question of the automorphisms of the elliptics of the.
I think they are. I think they're
surface.
very directly. I think I sort of tried to make that point before.
Can you do one of them? Can you show?
Well, like the 4 plus 4. I mean, the U2 that is. Well, am I claiming that that's like the Minkowski group? What are we trying to say?
That doesn't sound right. So like. So the square of the Gaussian elliptic curve will have a bunch of automorphisms, which are like, you can think of it like the group of 2x2 matrices that are invertible, that are in the Gaussian integers. I don't even know, what is that group? That's some finite group.
Well, but you can pretend that the Gaussian integers are just the complex numbers and get this larger thing.
Okay, that's what you want to instantly do. Yeah.
Yeah, I mean, I'm trying to convince ourselves that it is just this Minkowski thing and it's this,
Well, but I was trying to look at, okay.
You're trying to be more careful. You're trying to be more careful.
I was trying to look at automorphisms, which sort of, so like not all complex multiplication curves have extra automorphism. So I was trying to like be a little, I mean,
I think they do. They if I understand what you're saying, they all do have this, SL2 comma this thing with complex multiplication. Those really are they all give you some sort of automorphism group, right? I mean, we have those 2 Coxeter examples with the Gaussian and the Eisenstein case. The other ones we don't think are Coxeter groups, but we think they're sort of just as big or almost just as big. Almost just as big.
Okay.
Am I saying that right? I mean, SL2, comma the Kleinian integers, for example. I think that's big.
And so,
what do I mean? Let's see.
So how's it? So you're just going to have it act on c squared by multiplication. And then the Kleinian integers aren't, they're not a lattice. Wait, they're not a lattice in, I'm getting confused.
They're a lattice in C, yeah.
Okay, yeah, I keep screwing up with this dustiness versus non-dustiness. Okay, so they're a lattice in C. Okay, yeah, okay. Okay, so that, I'm really confused. Yeah, I'm confused why, like, so so the elliptic curve doesn't have any extra automorphisms when you use the Kleinian integers, but you're claiming the abelian surface does. That's what you're claiming.
I think that's what I'm claiming. Yes, yes.
Oh, okay.
Am I suggesting that this automorphism group is like, as a non-abelian group, that am I suggesting that it's co-compact inside the Minkowski group or something like that? I mean, does that happen for the Gaussian and Eisensteinian cases? And if it does, then I think I'm guessing the same thing for the.
Yeah, I'm pretty sure it is for those cases, and I never thought about these other cases nearly as much, but
I didn't think about them as much because I just hard to visualize, but I did think about them a little bit. I tried mentioning them to you a couple of times, but I think, they're not quite Coxeter groups, but I think you still get it. I still think you still get a tiling that's about it. So what is that word called? What is that? It's not the compact, right? It's some quasi-compact kind of Coxeter group or something. What is that called?
There's these paracompact. Yeah.
So maybe I'm suggesting that we still get, okay, but what does paracompact mean?
But that means, but that's not.
That doesn't sound good. It doesn't sound good enough.
That's not co-compact.
Right.
That's where you have lots of symmetries of a hyperbolic space, for example, that fix a ideal point at infinity.
Right.
So they're sort of.
But they must be, in some sense, not that bad. Is it that the tiles themselves are sort of almost compact or something like that? Even though the tile, let's see, what am I trying to say? Maybe that's part of it. Maybe it's a, non-compact space. It's got these cusps and things, but it's tiled by compact tiles or something like that.
I'm confused. Yeah, I mean, you have these. I don't know.
Yeah. Right. I'm throwing out a lot of random ideas here. I'm not even coming close to actually throwing out all of the random ideas that I want to throw out.
You've got.
Yeah, go ahead.
You've got 12 minutes to throw out more of them. So
that's
throw them out
that's
in
right.
approximate
So I've got a lot more to throw out at some point about motives
decreasing
and stuff
use.
like that, but I don't think that's really for today.
So start with the best idea. Tell me that, and go down to the next one.
Well, I think at the moment my mind is completely blank. But let me think where we are. So I mean, actually, I'm trying to blame you for there was some question here that you were sort of interesting question here that you were bringing up about something. I mean, what you're saying that we were
lots of questions.
Well, you're trying to compare these Lie algebras that I was talking about to the right. There's some very vague conjecture here that these automorphism groups in some case, right? You were looking at the right. There is some funny thing about how the complex multiplication does affect the symmetry group via this backdoor route involving the square of the elliptic curve or something like that, even though it doesn't affect the size of the symmetry group when you just have the Cartesian product or something like that. Let's see. All right. Okay. It's very disorganized. Let me try to think here for now. Let me try to think here for a minute. I mean, you can throw anything that you want to throw in as well. Let's see. I mean, I guess I did already say that, I'd like to know about the Boltzmann curve and these speculations that we're trying to come up with about connecting this Hurwitz's integral quaternions, see if they really do match up with the Boltzmann curve, the Jacobian of the Boltzmann curve, or if they don't, then what do they match up with? Oh, okay. So let me, right. You want some random ideas here? I'll throw out some random ideas. Okay. So again, it's nice to understand abelian varieties in general, but I actually really enjoy thinking about abelian surfaces in particular, because there's so much that should be very special about them. I mean, in a way that should be annoying to a generalist, but it's also very fun to a non-generalist too.
Specialist.
I don't like that word, specialist. It sounds general enough.
A specialist is someone who's interested in special situations of all sorts.
Okay, a general specialist. Okay.
Right.
So yeah, I keep on claiming that there are these three viewpoints about abelian surfaces that should be very closely related. Like, like they should almost be the same things as what? As hyperelliptic. Well, they should be almost the same things as genus 2 curves. Is that right? Genus 2 curves should be a lot like. Not sure
Todd
whether I
was
should say
trying to
polarized or principally polarized. Principally polarized abelian surfaces. What were you going to say? Sorry, what? Go ahead.
Todd was like,
Yeah.
trying to remember whether you had said that hyperelliptic, that abelian surfaces are the highest dimensional abelian varieties, that they're all Jacobians. Now you seem to be refining that to think that they're all Jacobians. Well, I don't know.
Well, I think
With
the
principal
point,
polarization, they all show up as.
yeah, don't trust me on any of
Jacobians.
this, but I think there's actually two big coincidences. Two sort of inclusions of moduli stacks or something like that, that both turn out to be very close to being invertible. And so their composite is also very close to invertible or something like that. So, I mean, you can take the Jacobian of a genus 2 curve, and that will be a polarized, I think a principally polarized abelian surface. And in general, that would be, in general for an arbitrary genus, that would be very far from being an invertible, but in the genus 2 case, I think it's very close to being invertible, very close in some sense. And then what's the other thing? Well, the other thing, I guess, is hyperelliptic or something like that.
Yeah.
So, right, there's the inclusion of hyperelliptic genus 2 curves into genus 2 curves.
Right.
And for other genuses, that is very far from being invertible. But in this special case of genus 2, it's very close to being invertible, I think. That maybe every genus 2 curve is hyperelliptic, or it's very close, that's very close to being true or something like that.
Yeah, I think that's true.
And the other thing is that every abelian surface is very close to being a Jacobian of a genus 2 curve, and necessarily, or almost necessarily, perhaps necessarily, of a hyperelliptic genus 2 curve. So yeah, right, yeah. I think these things are sandwiched together, and they're practically the same thing on both on the bookends. And but one of the slight glitches there is what I'm trying to say, that the squares, those aren't really Jacobians of genus 2 curves in general, I think, unless you include the degenerate genus 2 curves, the particular degenerate genus 2 curves which come from the self-joins of elliptic curves. Right, doesn't that seem approximately correct, that you can sort of think of a self-join of an elliptic curve as being an honorary genus 2 elliptic curve? And it's probably got a Jacobian in some straightforward sense, and that Jacobian is a square. It's the square of that elliptic curve. And this sort of exactly fills in the hole in the moduli stack. I mean, you know what I'm saying, right? I think that these squares of elliptic curves, those are ones that aren't Jacobians, unless you include these very degenerate curves that are the self-joins of the elliptic curves. Okay, I'm just making this up, but it sounds semi-plausible, doesn't it? What were you going to say?
Yeah, it sounds semi-plausible. You're making it sound like we should think of there being these like special cases of genus K curves that are like joins of lower genus curves.
Yes,
Maybe
yes, my wild guess
right?
is that is very much the case, and I don't know anywhere near as much about that as I would like to know. But if you force me to take a wild guess about some magic buzz name for that, I'll guess that has something to do with Fulton McPherson stuff.
Huh.
Were you suggesting anything else about that?
Nope.
But right? Isn't that something like they do in string theory, where they look at curves and they let them degenerate And it like corresponds to, I don't know, don't people think about that in a physicsy way? Didn't you try to teach me about that a long time ago?
Yeah, that was back when I knew something about it, but yeah, there's some.
All right. So,
There's some
so
stuff
I
like
don't,
that.
I don't know anything about it, but yeah, some vague ideas about where to try to learn that.
Uh-huh.
You know, maybe the Fulton-McPherson compactification, maybe the Fulton-McPherson operad. Maybe those have a lot to do with these smooth curves that degenerate into these non-smooth ones, maybe. And maybe that ends up being important in string theory and conformal field theory or something like that. I don't know. But so the last idea I'm trying to fit in here before we quit is, let's temporarily assume that this is on the right track, that you can sort of think of, you know, hyperelliptic genus 2 and general genus 2, well, hyperelliptic genus 2 and principally polarized abelian surfaces. Those are the bookends that you can, I'm claiming they're almost the same, and sandwiched in between them is the just general genus 2 curves. And those are, I think those are all roughly the same, unless I'm really screwing up here or something.
Uh-huh.
And then the last vague idea here to think about for today is to think about how these degeneracy themes that we've been thinking about, think about how those show up in all three of these perhaps roughly equivalent pictures. So think about how, you know, think about, right, over at one extreme, you can think about how hyperelliptic genus 2 curves, how they want to naturally degenerate. And you can compare that to over on the other extreme, how the principally polarized abelian surfaces, how they naturally want to degenerate. You can try to get these two things to match up with each other, or you can perhaps discover that they don't match up with each other very well. But I have some vague feeling that they do match up with each other in interesting ways. So part of the thing about the things about the hyperelliptic genus 2 curves, if I'm understanding correctly, that's, I mean, another way to rephrase that, roughly speaking, is you could say that that's like studying quintic polynomials or monic depressed quintic polynomials or something. Just like, you know, elliptic curves are about monic depressed cubics.
Uh-huh.
Right? Those are elliptic ones. Hyperelliptic ones are, you know, where you're taking the square root, the double cover or whatever of something that has more poles. So in this case, you know, instead of, right, this is the case where instead of having the Riemann sphere with 4 points on it, we now get the Riemann sphere with 6 points on it.
Yeah.
And so you can think of the way that a 6-point subset of the Riemann sphere, what are the ways for that to degenerate? And I don't know, but very roughly, it seems to me like it, well, for one thing, what am I trying to say? 2 of the 6 points could collide.
Mm-hmm.
And then once you've got 2 of the 6 points colliding, you could go one more level of degeneracy by having them 2 of those points collide. So you're just down to 4 points or something like that. And if you keep track of the dimensions of these little parts of the moduli stack, those very vaguely remind me of what happens over on the other extreme when we're keeping track of the abelian surfaces with the principally polarized abelian surfaces. So, I mean, right, the first big level of degeneracy is the products. That's a codimension 1 constraint, a codimension 1 substack or whatever. The ones that are products. That's a 2-dimensional thing in this 3-dimensional modular stack. And then one level beyond that is the squares, and that's another codimension. And very vaguely, I mean, I'm just saying it's tempting to try to get those to correspond to each other. It's tempting to try to get these product things to correspond to the 6 points degenerating to 5. And then getting the squares to correspond to these 5 points degenerating to 4. Because right when 5 degenerates to 4, that sounds like you've got an elliptic curve, 4 points on the.
It's true. That's good.
And if you've got 5, then I'm trying to squint at that and sort of think of it as 2 4s stuck together. Because right, if you just have 3, there's not even any modulus in that, right? That's just right. It's triply transitive or something like that. So it's really the 4th point where you start counting, getting extra modulus. So I'm trying to picture it somehow as these 5 points is giving us somehow get that to correspond to a product of product of elliptic curves. And
so
get that, yeah.
So if this is the way you're going, then the Bolsa curve where the points are in an octahedron, that's like completely generic.
That's generic from that point of view, but that's just like with the elliptic curves, right? I mean, so with the elliptic curves, the degeneracy where the points start colliding with each other, that only gives us the cusps. But there are these other kinds of degeneracies or whatever you call them, where the points start forming a symmetrical arrangement. And if it's a regular tetrahedron, then you're getting the Eisenstein thing. Whereas if it's 4 points around equally spaced around the equator, then that's the Gaussian thing. So yes, right, you have, in addition to there are these very gross kinds of degeneration where the branch points actually start colliding. That gives some very gross kind of, and that involves a continuous modulus or something like that. But then there are these more delicate things involving the discrete symmetry. And those are, right, so somehow these, there's a sort of like a continuous kind of degeneracy and discrete kind of degeneracy, and they're somehow both probably very important to understand the moduli stack. And I don't know, I'm already out of time. But I think I sort of gave you a vague hint of some of the things I'm thinking about here.
Yeah, that's nice. It sounds sort of like you could try to think of like some moduli stack of bunches of points on the Riemann sphere, but where you also like keep track of the automorphisms of the Riemann sphere as like part of the story. So is it true that like it's like the octahedron like? So like the octahedron is probably like a specially symmetrical. I mean, it's obviously specially symmetrical, but I guess it's even specially symmetrical, not with respect to rotations, but with like maybe with respect to SL2C acting on the Riemann sphere. That is, it's not true that like all 6 point configurations are equally good as far as the action of PSL2C on them goes. Some of them are have bigger stabilizers than others. So it could be like the octahedron.
Yeah, but I think whatever that Boltz's symmetry thing is, that is probably that.
Yeah.
That subgroup of 6 bang that you're talking about.
Yeah. So anyway, yeah. So you could, if you thought of some kind of stack where you put in the SL2C action into the stackiness, then you could maybe account for both the kinds of degeneration here. Anyway, it sounds like lots of fun to think about.
All right. I get a very vague sense of what you're hinting at, but I'll have to think about it. So yeah, all sorts of stuff I wanted to say about motives, which is way vaguer in my mind than any of this. So that's one excuse for not getting to that. All sorts of stuff I wanted to say about complex multiplication. And we did get it a little, right? We've already been sort of talking about complex multiplication, but there's a whole bunch of other things to talk about complex multiplication, Jugendrum, and stuff like that. And we haven't gotten into that yet. I mean, there are just so many things to talk about, and it's very hard to get to any of them. But this was very helpful today. Again, I won't figure out until later all the things I forgot to say today. But at the moment, I can't think of anything else. But I guess we're sort of ready to quit here. I hope we didn't go over too much. And yeah, so thanks a lot.
Yeah.
And hopefully I'll see you again next week or something like that.
Yeah, next Monday I have to give a talk at 6 in the morning because it's for this applied category theory conference in Glasgow that I'm And so I can probably talk, but maybe you have to take a nap before I talk.
Sure. Well, I was going to suggest whether I could use that as an excuse to try to monopolize the conversation again. But
yeah,
say it
well,
again, you're talking to people in Glasgow, but you're talking to them from
Riverside,
from California.
Therefore,
From Riverside.
Therefore, from my point of view, I have to talk at 6 in the morning, and so
6 in the morning. 6
it's
in the
not
morning.
good. I have a
Only 6 in the morning. Okay, that's fair enough.
So
Okay,
yeah.
okay. Or if you need to rearrange anything else, you can just try to let me know as early as possible. I think I'll be fine for 4:30 p.m. next week. I think I'll be awake.
Yep.
And
Okay.
it sounds like you might be awake too.
I'll probably be awake. If I sleep, it'll be before then, probably.
Okay. Okay.
Or right
Okay.
after then or something. Okay.
Okay.
I'll see you.
Okay. Thanks a lot. Bye.
Yep. Yep. Bye.